Okay, now that we've already gone over the equations that govern the motion of projectiles that follow half parabolic trajectories, let's cover full parabolic trajectories. So I want to consider the case maybe where you kick a soccer ball across a level field. So it's clearly going to rise and fall and reach some maximum height. We'll call that h. We can put a subscript max for maximum height, because of course this would also be some sort of height, but not any special value. The horizontal distance from where it's kicked to where it lands is once again known as capital R for the range of the projectile. And then some things to note about this. There's symmetry to it if the ground is level. So here's some symmetry. The time to rise is equal to the time to fall. If we take the initial velocity indicated here, right, this vector, and break it into components, part of its velocity causes motion along the x-axis, and part of that motion at an angle produces an independent motion along the y-axis. So that initial horizontal component to the overall speed remains constant throughout the entire motion, and the initial vertical one is affected by gravity. In the end, the ball is going to land with an overall velocity pointing down and at an angle into the ground. Whatever the initial angle was will match the final angle of impact with the ground. Whatever initial horizontal speed it had to begin with, it maintains just before striking the ground. And whatever initial upward vertical velocity it has right when it takes off is the vertical velocity at impact at the moment it strikes the ground. Okay, so yeah, the symmetry, the time to rise and the time to fall takes off at the same angle it lands at, and it returns with a vertical speed that matches the vertical speed it had at the start. Let's go over this in a little more detail. So the trajectory shown here is a full parabola. And if we make a few dots along the way, let's picture when the soccer ball gets to point 1, point 2, point 3 at the very top, 4, 5, and 6 is just before it strikes the ground again. And here we want to show the components of the velocity. So the overall true speed is shown here, directed at some angle. If we make a line that goes parallel to the ground, then we can define the angle at which the ball was kicked. We'll give it the symbol theta. So we have the initial horizontal component. And notice I'm building a right triangle out of the velocity vectors. If I make a line that goes horizontal, that can help me construct the initial vertical component to the velocity. So the length of the velocity components, both the horizontal velocity component and the vertical velocity component, the length of those vectors is established by making a parallelogram. And then we can see that the components really just form the sides of a right triangle. Okay, so the length of this horizontal component of the velocity is unchanged throughout the entire flight, simply because there is no acceleration, there are no forces to produce an acceleration along the x-axis. Of course, again, we're ignoring air resistance. If there were air resistance, that vector would be getting shorter and shorter and shorter along the way. But we're assuming free fall, where gravity is the only force acting, and because gravity is applied downward in the vertical direction, it has no influence on the horizontal component of motion. So a continuous, constant, horizontal velocity, sorry, that last one went off the screen, so I'm not going to draw it in. Now the vertical velocity is affected by this force of gravity, so if that upward velocity is described by the length of the vector, we're going to see that vector get shorter and shorter. We'll draw this one in green. So maybe when it gets to this point, the upward component to the speed is a little less. When it gets here, a little less still, and at the very top, the vertical component to the speed is equal to 0. And then as it starts to fall back down, it gains a little bit of downward vertical velocity, gains a little more, and then at impact has the same downward component of velocity as it had to begin with. Okay, in fact, there's a website. It's called PhET. Not sure what that stands for. I believe it's put out by University of Colorado, and it just includes a lot of online simulations of physics principles for all subjects: electricity and magnetism, optics, vibrations and waves, and also a few in Newtonian mechanics, and one in particular is a projectile motion simulation. So, in fact, if you type in any subject in physics, so for example, projectile motion, so in Google, right, or any search engine, if you enter the subject and then you add the phrase applet, then you'll find some websites that have embedded simulations. Some of them use Flash, some of them use Java. I'm not really great at computer languages, so there might be other ways that they code so that you can run some sort of animated simulation of physics principles. In fact, when an applet is used to make physics principles come to life, they sometimes refer to it as a physlet. So I'd encourage you throughout the semester to find some physlets just by typing in any subject matter followed by the word applet or physlet. Okay, so that was a little bit off topic. Let's bring this back home. So in the next video segment, I think what I'll do is screen capture myself kind of fooling around with the PhET physlet for projectile motion. And you'll see exactly what I'm talking about in animated fashion regarding these changing vertical velocity vectors and constant horizontal vector components. Okay, given that picture, then will that help guide us in determining some equation that'll describe what the time of flight should be for a projectile of this nature? All right, we're going to follow the advice of treating horizontal motion and vertical motion as two separate and independent types of motion. So the time of flight, I think we can figure out based on just the vertical motion alone. Okay, so we know from the symmetry, we can divide the motion in half. For part of the time, it's rising, and for the other half of the flight, it's falling, and those two times are equal. So if I want to get the total time of flight, I can just multiply 2 times the time that it takes to fall. So let's consider that. If I'm only highlighting the falling portion, then I know at the beginning the vertical velocity starts out at 0, and in the end the vertical speed is just as great in magnitude as it was when it was first kicked. So initial velocity equals 0, final velocity is equal to the same amount as the initial vertical velocity. The acceleration is acceleration due to gravity, and we're trying to find the time. Now notice, we're not interested here in how far it fell. We'll get to that, but that vertical displacement that we'll end up giving a name to, just call it h, that can be solved for later. So we basically want an equation that ignores displacement. So the equation we're looking for here is final velocity equals initial velocity plus acceleration times time. So in this case, we have v naught y equals 0 plus gt. Of course, this is just the amount of time it takes to fall. So if we rearrange and just divide both sides of the equation by g, then we find that the time it takes to fall is just equal to the initial vertical component of velocity divided by g. So the total time is 2 times the initial vertical velocity divided by g. Okay, well, in problems like this, most likely you're not going to be given the value of the velocity components. What you'll be told is the overall speed and the angle at which it was kicked. But I want you to notice, and I know this is getting a little bit sloppy, but there's a right triangle in here. The total speed at an angle represents the hypotenuse. The horizontal component to the speed represents one side, the side adjacent to the angle, and then the vertical component to the speed represents the opposite side of the right triangle. So let me draw that out a little better. So there's the initial horizontal component to the speed. There's the initial vertical component. And how about we do this in red? The overall velocity is at an angle. I think the notation I like to stick with is the true original vector. And vectors should always have an arrowhead on them so I can distinguish the difference between pointing down and to the left and pointing up and to the right. So yeah, if I have a total closed arrowhead, I guess that's my way of illustrating the original vector. And then when I draw in the components, I put an arrowhead on it, but it's an open arrowhead. So that's just one way that you can help distinguish between vectors and the vector components that they can be broken down into. All right. So we have the angle theta, the total speed, just indicated by v, and then we know from trigonometry, SOHCAHTOA. Don't think we need to concern ourselves with the tangent of the angle, but basically what we're saying here is the sine of the angle is equal to opposite over hypotenuse. So let's write that out a little more clearly. The sine of this angle theta should be equal to opposite over hypotenuse. So this should be equal to the initial vertical speed divided by the true total speed. And likewise, cosine equals adjacent over hypotenuse. So cosine theta is equal to adjacent over hypotenuse. On both these equations, it might be helpful to multiply each side of the equation by v. Okay, if I do that, then the v cancels out. And what we really have is then we can always find the vertical component to the speed by taking the overall speed and then just multiplying it by the sine of the angle. And likewise, if I want to find the horizontal component to the speed, I multiply the total true speed times the cosine of the angle. So v naught x is equal to v cosine of theta. And this should make perfect sense, right? Imagine a case where the ball is kicked at a really, really low angle. Then we would expect that the vertical component would be very small in magnitude. And of course, the sine of angles that are close to 0 give very small values. And likewise, the cosine of an angle very close to 0 gives a very large value, which is what you'd expect. So in other words, at a low kick, when the true overall speed is directed at some very low angle, then you have a long horizontal component to the velocity and a very short vertical component. And we can see that the sine of a small angle is a small number and the cosine of a small angle is a large number. And then conversely, if you were to kick it at a very steep angle, then the horizontal component is small and it's the vertical component that's large. Okay, so that allows us to make a substitution, right? In our equation for time, we have just the vertical component to the speed, but we can substitute for that the total speed times the sine of the angle. So in the end, how about we scratch this out and call it like this. The total time, which is double the time to fall or double the time to rise, is equal to 2 times v sine theta. So v sine theta is just a way of replacing v initial y, all divided by g. And then I suppose I don't really need these brackets here, right? That doesn't doesn't do anything for us. Yeah, there. Okay, so another thing you might be interested when something follows a full parabolic trajectory is not just how much time it's going to spend in the air, but you certainly might want to figure out how far away it's going to land. So in that case, let's focus on the horizontal motion. So we're going to use the equation delta x equals v naught t plus 1/2 at squared. All right, it would be a mistake to replace that a with g because there's only an acceleration of gravity along the y-axis, but we're treating horizontal motion as independent from vertical motion. So in fact, this a is a subscript x, which is 0. There is no acceleration along the horizontal axis. That whole part of the equation goes away, and we're left with delta x equals v initial in the x direction multiplied by time of flight. And now we can make substitutions for both of these terms. Okay, we know we can substitute for t. It's what we derived in the last step. And what we can substitute in for v naught x comes from the trigonometry we just performed. The initial horizontal speed is the total speed when it's kicked times cosine of the angle. So let's put this all together. Oh, and of course, I'm going to replace delta x with the symbol r, right? The horizontal displacement is known as the range. So our range is equal to v cosine theta. That replaces v naught x. And then we'll replace t with the expression 2v sine theta over g. And we should simplify this. So let's see, we've got a v multiplied by a v. That's going to give us a v squared. So we get v squared times, and we'll put the rest together, 2 cosine theta sine theta. 2 cosine theta sine theta, and then all that divided by g. And then some of you probably picked up on something familiar here. Do you sniff this out? If you were good at committing to memory a lot of your trig identities, then you might recognize 2 cosine theta sine theta as the double angle formula, right? I can replace that with just sine of 2 theta. So in the end, we have an equation for range. It says r equals v squared sine 2 theta over g. Now be careful, when you look at this equation, there's some similarities with the equation for time, right? We see the sine function appear in both. Although one of them is sine of theta and one is sine of 2 theta. Both of the equations have g in the denominator, and they both have a v, although this one has a v to the first power and this one has a v squared. And there's also a 2 in both the equations. There's a 2, and in this one the 2 is associated with the angle. Okay, so sorry for messing these up. Let me write them again neatly. Total time of flight is 2 v sine theta over g, and the full range is v squared sine 2 theta divided by g. There's something peculiar about this part, about taking double an angle. I'll comment on that in a moment. Turns out there's something noteworthy about projectiles that are launched at complementary angles, meaning any two angles that add up to 90 degrees, right? If you were to project something at 10 degrees across level ground and then at 80 degrees, keeping v the same in both cases, or 30 degrees versus 60 degrees, or 15 degrees versus 75 degrees. Basically, any two angles that add up to 90 degrees, complementary angles. I'm getting ahead of myself. Let's figure out the maximum height. So yeah, these are the things you would want to know, right? If you kick a soccer ball, how far away will it land? How much total time will it spend in the air? And what's the highest displacement it's going to have vertically above the ground? So for maximum height, again, we want to study the vertical motion, disregarding any horizontal displacements. So how about in this case, again, we just look at the portion where the projectile is falling. So instead of studying the entire motion, let's cross out the first half while it's rising and then just highlight the second half. So again, we can employ this trick that the initial velocity vertically starts out at 0 when it's at the very top, and then has some final velocity when it hits the ground that's equal to whatever the initial component of the vertical velocity was. All right, and now we're trying to solve for delta y. So initial speed, final speed, acceleration time, and displacement. So the initial speed is 0. The final velocity is the same in magnitude as the initial upward velocity. The acceleration is g. And in this regard, we can leave out the time, I suppose. So we use the equation that doesn't involve time, that says final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. So if we're applying this just to the vertical motion, independent of horizontal motion, we can put subscripts y. We don't have to say a subscript y. We know that that's the same thing as g. And then instead of calling it delta y, let's just call it h. So the initial speed is 0. We can cross out that term. So to solve for h, we just need to divide both sides of the equation by 2g. So we find that h is equal to vy squared divided by 2g. Then we're going to make that substitution one last time, that vy is the same thing as v sine theta. So we have, let me make some room here, see if I can move all this, there we go. H, let's keep in mind this is H maximum, is equal to v sine theta quantity squared divided by 2g. Or maybe that's better written as the maximum height is equal to, so this means we're squaring both the v and sine theta. So we have v squared sine squared theta over 2g. So again, I'm going to caution you, the best approach to knowing these equations is certainly not to try to memorize them, because you're going to end up making some mistakes. Look how similar all three of these equations look. The equation for maximum height, the equation for range, and the equation for time, they all have g in the denominator in some way. Two of them just have g in the denominator, and one of them, a maximum height, has a 2g in the denominator. So there's 2's that show up, right? There's sine of 2 theta in this equation. There's a 2g. I guess we can think of the 2's that express quantities are squared. In a couple of the equations, there's v squared. In one of the equations, there's just v to the first power. There another 2 showed up. In all of them, we see sine theta. Here's sine of theta, here's sine of 2 theta, and here's sine squared theta. So trying to memorize these is going to be very daunting. But you can see that it really wasn't a lot of mathematical steps to derive these from fundamental equations that you probably have already memorized. You've no doubt memorized this kinematics equation, and there's no doubt you've memorized this kinematics equation by now, or for that matter, this kinematics equation. And so from a few basic kinematics formulas that you've committed to memorize, committed to memory, you can do a couple steps of algebraic work and derive these other equations. So that's a more powerful approach to physics, is being able to derive important equations as opposed to just memorize them. So why is it true that complementary angles share the same range? Well, let's look at this equation for range one more time. The range is equal to v squared times sine of 2 theta divided by g. Okay, well, I just encourage you to grab your calculator and pick any two angles that add up to 90 and find out what the sine of 2 times that set of angles would be. I'm going to try it on my calculator right now, and I'm not going to pick a pair like 30, 60, because those are special angles. There might be some sort of coinky-dink there. Let's just pick at random some like really awkward complementary pair of angles. So let's see what happens if we take something like 23 degrees, and then what would be the complement to 23 degrees? That would be 67 degrees, right? Okay, so then 2 times 23 degrees, that's what we're interested in here, is double the angle, would be 46 degrees, and 2 times 67 degrees would be 134 degrees. So I'm curious, what's the sine of 46 degrees, and what's the sine of 134 degrees? So I'm grabbing my calculator right now, and I'm going to try this. You can play along at home. The sine of 46 degrees is 0.719. 134 degrees, take the sine of that, and lo and behold, that's 0.719. Okay, so you can try this with other angles and convince yourself, but you've probably learned that before in a math class years and years ago. So if that's the case, then what we're saying is there's 2 ways to get projectiles to land in the same spot. So let's say there's some sort of contest. Maybe you're at the carnival, and the trick is to try to fling something. So you're standing here at a counter, and you've got this little device that you push a button, and a little object goes flying through the air, and then it has to land in a dish over here that's sitting on a table at the same height. So one way you could do it would be the lower angle in that complementary pair. So maybe that's 10 degrees. And then the other option would be at 80 degrees. Of course, 10 degrees and 80 degrees add to 90 degrees, right? They would both land the same distance away. Now, that's not to say they'd spend the same amount of time in the air. Not a chance, right? The one that's launched at the greater angle is going to spend more time in the air than the one at the low angle, but they still land the same distance away. All right. Let's try a couple example problems and put these formulas we've derived into practice here. A soccer player attempts to kick a ball over a fence that's 5 meters tall. They kick the ball at a location that's 30 meters away from the location of the fence, and the person kicks the ball with an initial speed of 20 meters per second, and the ball flies away from the ground at an angle of 60 degrees. Let's picture this before we get too far into it. So here's our level ground. All right, and then we'll put the velocity vector in purple. How's that? So I choose a vector this long to represent a speed of 20 meters per second, and then indicate that the angle is 60 degrees. So there's V, there's theta. And without a doubt, it follows this full parabolic trajectory and strikes the ground somewhere. Well, maybe it doesn't strike the ground. We don't know about that. See, if we read this problem again, it's telling us that there's a fence in the way. So somewhere downrange, at a distance of what, 30 meters away, there's a fence that's 5 meters tall. Now, this first question, express the initial velocity vector in what's called unit vector notation. Okay, so there's another way of saying that you kick a ball 20 meters per second at an angle of 60 degrees. Okay, actually what I'm giving here is not just the speed, but the velocity, because I'm giving magnitude and direction. Well, another way to express the velocity as a vector is in what's called unit vector notation. Now, hopefully you've learned this already in one of your math classes. If not, you'll encounter this certainly in your math course this semester. If you have a vector quantity that lies along the x-axis and just happens to be exactly 1 unit in length, there's a name for that vector. They just name that, I don't know who chose this, but they call it I hat. There's another named vector that we're interested in two-dimensional space. If there's a vector exactly 1 unit long, along the y-axis, the name for that vector is j hat. So what we could do is take any vector. Let's say there's a vector, well, just like this soccer ball, that's 20 units long at an angle of 60 degrees. We know we can represent the components of that velocity by using the parallelogram method and deconstructing the vector into its components. So there's a horizontal component, and of course there's some vertical component. Now those components are longer than 1 unit, so neither of these components are the familiar vector I or the familiar vector j, but there's some scaled up amount of that, right? Like how many multiples of this vector I can be strung end to end before they're just as long as the horizontal component of v? And how many of these vectors j can be placed end to end so they build up the vertical component to the velocity? So that shouldn't be too hard to figure out. What we're really asking for is what is the length of the sides of a right triangle. So we've got the length of the hypotenuse is v. We know the angle is theta. We'll keep it general. I know in our example the v is 20 meters per second and the angle is 60 degrees, but just to generalize this, I'm certainly allowed to take this purple vector. Let's see if I can do this. If I grab hold of that and slide it over here, you see it has the same length no matter where it goes, right? As I move a vector around, I don't really change the vector by putting it in a new location. The only way to change a vector is to either rotate it or stretch it. So I can take, well, all I'm saying is I can take that pink vector that represents the vertical component, and it's the same vector when I draw it in over here, right? Not so much a matter of where the vector is located as it is just how long is the vector and what direction does it point. And the reason I want to do that is just so we can see now I've got a right triangle. Okay, so same thing really we had before. SOHCAHTOA. Sine equals opposite over hypotenuse. So sine theta equals Vy over V. Multiply both sides by V, and we have Vy equals V sine theta. And likewise, without showing you every step along the way, if I use the fact that cosine of an angle is the ratio of the adjacent side over the hypotenuse, it's easy to show that the horizontal component is V cosine theta. Okay, so what I can do is just say that the overall velocity v pointing at an angle is composed of two components that are added together. There's a horizontal component and a vertical component added together. So I'm going to put a plus sign. And the length of the vertical component in magnitude is computed by multiplying the magnitude of the overall velocity by the sine of some angle. And then if I were to multiply that times the vector I hat, that's really the same as just multiply by 1. Okay, and multiplying by 1 doesn't change the magnitude of your result, but because I'm multiplying it by a quantity that has a direction to it, I'm turning the component itself into a vector. So the overall vector is v cosine theta multiplied by I hat, and then in the same way combined with v sine theta multiple of j hat. So one way to represent velocity as a vector is to give magnitude and angle. The other way is in what we call the unit vector notation, which is this second approach. And in this case, hey, grab a calculator and see what you get. Specific to this problem, we could say the velocity is, well, let's just multiply it out. What is 20 times the cosine of 60 degrees? Oh, well, wait, 60 degrees is a special angle, right? Cosine of 60 is 1/2. So this is 10 meters per second I hat plus, okay, the sine of 60 degrees multiplied by 20 gives us 17.3 meters per second j hat. Okay. So two ways of giving the same information. Option number 1 and option number 2 are both a way to tell us not only how fast, but how fast and in what direction. What this is really telling me is since the component that corresponds with I hat is smaller in magnitude than the component associated with j hat, then that's a way of indicating that the angle must be greater than 45 degrees. Now, I can't really tell off the top of my head that that implies 60 degrees, but with a little bit of work, I'd be able to figure that out, right? So if the angle were exactly 45 degrees, then these components would be equal to one another. All right. That was a long answer to this first question, wasn't it? Express the initial velocity in unit vector notation. There it is. V equals 10 I hat plus 17.3 j hat. Does the ball clear the fence? Well, that's going to take a little effort on our part to determine. Well, I've got a second question waiting for you here. Let me get this out of the way. We need some room to work here. Okay, so back to the picture. Well, we know when it gets to the fence, there's no guarantee that 30 meters is the range. There's nothing in the problem that says 30 meters is how far away it lands. In fact, it could be that it's rising, reaches its greatest height, and then hits the fence. It could be rising, reaches its greatest height, and then on its way down, clears the fence. Or it could be it's rising, 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 still hasn't reached the plane of the fence yet, then reaches its maximum height, then comes down. So whether it's A, B, C, or D isn't clear based on the information given in the question. It's up to us to figure it out. So let's just say by the time it gets to the plane of the fence, whether it's condition A, B, C, or D, it will have traveled a horizontal displacement of 30 meters. I'm not going to call that R because 30 meters isn't necessarily, the only way 30 meters represents the range is if it's for sure case A. And here, spoiler alert, it ain't case A, all right? Sure, so I don't call 30 meters R for range. I just say it represents some amount of horizontal displacement. So delta x equals 30 meters. The horizontal acceleration is 0. Maybe we can figure out how much time it takes to travel 30 meters. I know the horizontal velocity is equal to, well, that's all this is right here. This 10 meters per second is the initial horizontal velocity, and the 17.3 meters per second represents the initial vertical velocity. So v initial x is 10 meters per second, and we could just use the equation. Well, final velocity is also 10 meters per second, right? Horizontally, the velocity doesn't change at all. All of these components are of the same length. So delta x equals v naught x times t plus, I'm going to say 1/2 at squared, but then immediately cross that out because the acceleration is 0. And because the acceleration is 0, that's why the initial and final speeds are one and the same. So it's just the dirt equation once again. Distance equals rate times time. So the time that it takes to reach the plane of the fence is equal to the distance to the plane of the fence divided by the horizontal speed. So this is 30 meters divided by 10 meters per second, which gives us a time of 3 seconds. So whether it strikes the fence, clears the fence while it's falling, or clears the fence while it's rising, whichever case that is, the one thing we know for sure is by the time the ball has reached the plane of the fence, 3 seconds will have elapsed. So to determine whether or not it clears the fence, now we need to know what its vertical position is 3 seconds after it was kicked. So this is exactly the advice in all types of projectile motion, right? We're treating horizontal displacement as totally independent of the vertical displacement. So let's see, what do we know about the vertical motion? The initial vertical speed is 17.3 meters per second. Final vertical speed, we don't know. I have no idea how fast it's moving along the y-axis when it reaches the plane of the fence. Whether it's this case, or this case, that's an unknown. So I bet we're going to try to use an equation that doesn't involve final velocity, okay? The time is 3 seconds. The acceleration is, hey, I skipped a very important step here. I've left out my frame of reference. So there's my origin along the y-axis, and I'm going to choose, I'll choose up is positive and down is negative. That's sort of the conventional approach. So if that's the case, I mean that the initial vertical velocity is positive 17.3, and the acceleration is due to gravity pointing downward, so it's negative 9.8 meters per second squared. And then we'd just like to find what's its vertical displacement during that 3 second interval. So we're using the familiar equation delta y equals v initial y times time plus 1/2 at squared, and we'll replace the a with g. So we get delta y is equal to 17.3 meters per second times 3 seconds plus, let's see, half of g would be 4.9, right? 4.9 meters per second squared times 9 seconds squared, right? Plug in 3 for t and then square it. So not only are we squaring the 3, but we're squaring the units of seconds. So seconds squared cancel with seconds squared. Here, seconds cancel with seconds, so we're adding meters with meters. That's good. 17.3 times 3 gives us 51.9 meters, and then 4.9 times 9. Oh, you catch my mistake? This is negative 4.9, isn't it? Yeah, because this was negative 9.8. Okay, so 51.9 meters minus 44.1 meters. And we get a value of positive 7.8 meters. But we know the fence is only 5 meters tall, so we just ruled out B as a possible trajectory. We know it clears it, right? In fact, we know it clears it by a height of 2.8 meters. So if we look at this question, does the ball clear the fence? And if yes, by how much? So the answer is yes, and it clears it by 2.8 meters. So is the ball rising or falling? Is it this option or is it this option? Well, what we really need to know is when it reaches the plane of the fence, is the vertical component to the speed pointing upward, or is the vertical component to the speed pointing downward? In other words, is it positive or is it negative? So treating vertical motion as independent from horizontal motion. Again, studying just along the y-axis, we can apply the equation v equals v naught plus at. So the velocity after 3 seconds is equal to an initial velocity of 17.3 meters per second plus negative 9.8 meters per second squared times 3 seconds. That gives us a value of 17.3. Well, if we round up, right, and say this is almost equal to 10, then this whole thing is going to be very nearly negative 30, and negative 30 combined with positive 17.3 is going to be a negative value. So without getting an exact answer, it's very clear to see that it reaches the fence while it's falling, because after 3 seconds, at that moment, the velocity no longer has a positive value, it has a negative value. So this is the most accurate representation of the motion of the soccer ball as it just barely clears the fence. What's the maximum height reached by the ball? So it reaches a height of, that's a height of 5 meters. At the moment it reaches the plane of the fence, it's at a height of 7.8 meters, but that does not tell us what the maximum height is. So we just need to use the equation that we derived earlier in this lesson for maximum height. Okay, now we know all these equations for time, range, and height. Gosh, they all have v or v squared in the numerator. They all have g or 2g, and which one is which? So by now you shouldn't have these memorized, I wouldn't expect. The maximum height is equal to v squared v squared sine squared theta over 2g. That's my guess. Let's go back up and see if I got that right. Maximum height, v squared sine squared theta over 2g. Was that my guess? V squared sine squared theta over 2g. How did I know that? Well, I've been doing this for a long time. I have committed it to memory, but not by choice. There's just kind of no way around it if you've done this for long enough. But that really just comes from the equation v squared equals v naught squared plus 2g delta y. And we replace delta y with h. So we have, based on the symmetry, we can study just half of the motion, right? Just the falling portion. So we have h equals v squared over 2g, but the vertical component of the velocity can be substituted with v sine theta. So we have v sine theta quantity squared over 2g. And that means both the v is squared and the sine theta is squared. So this is where v squared sine squared theta over 2g comes from. If we plug in the given values, now what are we plugging in for v squared? You might be tempted to plug in 17.3, but that's vy, right? So we could shortcut it and just say 17.3 meters per second squared divided by 2 times 9.8. Or if we're actually plugging in what's suggested by this equation, this v means the total velocity of 20 meters per second. And then we're going to take the sine of 60 degrees and square that, and then divide that by 2 times 9.8 meters per second squared. But the end result is when, and this 20 is squared. So when we do 20 squared multiplied by the sine of 60 degrees squared, that's going to give us the same thing as if we were to just square 17.3 to begin with. All right, so grab your calculators, whichever way you do it. Let's see what we get. See if we can both get the same answer here. Okay, so I got h max is equal to 15.3 meters. So if you got a different answer, That means one of us made a mistake. Okay. This is turning into a long lesson. How far downfield would the ball land if there was no fence at all? Well, why does it say that? Whether there's a fence or not, since it clears it by 2.8 meters, how far downfield does it land? Now that's the range. And our range equation is R equals v squared sine of 2 theta. That's not sine squared of theta. That's sine of double the angle divided by g. So this is 20 squared. I'm going to leave out the units this time. Shame on me. So 20 squared times the sine of 120 degrees divided by 9.8. And it comes out to 35.3 meters. So it just barely clears the 5-meter tall fence, and instead of landing 30 meters away, lands an additional 5.3 meters beyond. All right. Let's just do one more problem before we wrap up this rather long lecture. A physics student, in an attempt to learn about projectiles, makes their own potato cannon, and the very first time they launch it, they measure it and they find out it takes 6 seconds in the air, and it lands 96 meters downfield. So what angle was the potato cannon launched at? So these potato cannons, yeah, they're made out of these rigid ABS, which is kind of like PVC pipe. It's a little bit thicker and a little bit stronger, so less likelihood of failure and injury. So there's the combustion chamber. There's usually a little bolt that's drilled through here so the chunk of potato can't fall into the combustion chamber. And then there's always some sort of trigger mechanism, and an explosion goes off in here, and the expanding gases push the chunk of potato out, and it goes flying. Okay, and so the time of flight is 6 seconds. That means the time to rise is equal to the time to fall is equal to only 3 seconds, right? That's the nature of the symmetry of this sort of motion. And the range is 96 meters. What's the launch angle and what's the speed? Okay, so you might think, well, we know the range, so we can apply that to the range equation. Range is equal to v squared sine of 2 theta over g. And we know g is 9.8. And now we know the range is 96 meters. But the problem with this is if we try to solve this equation anyway, now there's two unknowns. We don't know the value of v. We don't know how fast the potato came out of the barrel, and we don't know what angle it was launched at. So we can't use this range equation to solve for anything. So we're going to need another approach. And this is very straightforward. Look, the horizontal speed stayed the same the whole time. And horizontally speaking, it traveled a distance of 96 meters in a total time of 6 seconds. So we know that the horizontal component to the speed is the horizontal displacement divided by time. So if we use the full range, then we're using the total amount of time. So this is 96 meters in 6 seconds, and 96 divides evenly by 6 to give us 16 meters per second. For the vertical speed, we can use the equation, how about v final in the y direction is equal to v initial in the y direction plus acceleration times time. And then we can just choose, do we want to focus on rise or do we want to focus on fall? It's up to you. Well, I suppose it's up to me since I'm the one solving this problem here. So here's what I'll choose. I'll choose the fall. Okay? So that the initial velocity is equal to 0. So that part of the equation goes away. And then we just get that Vy is equal to gt. So because I'm only looking at half the motion, just the falling, then this time is not the total time. This is the fall time of 3 seconds. So if I multiply 9.8 meters per second squared times 3 seconds, I get, what is that going to be? 29.4 meters per second. So we've got the horizontal speed and the vertical speed, and keep in mind when a velocity vector points at an angle, the horizontal speed and the vertical speeds just represent the sides of the right triangle. So v should be equal to the square root of vx squared and vy squared. In other words, v should be the square root of 16 squared plus 29.4 squared. Which gives a total of about 33.5 meters per second. Oh, we've answered B before we answered A. We found the speed, we need to find the angle. So to find the angle, TOA, SOHCAHTOA, TOA. Tangent equals opposite over adjacent. So the tangent of the angle we're after should be equal to the ratio of 29.4 over 16. Of course, if the units are the same in both the numerator and the denominator, there's no point in including them to begin with. So 29.4 divided by 16 is equal to 1.8375. So to get the angle, we need to take the inverse tangent of 1.8375. And that gives us 61.4 degrees. Okay, hey, that was a long one. Thanks for tuning in.